Hi, I'm Themis Gouleakis, and I will talk about simple local computation algorithms for general Lovasz local lemma. This is joint work with Dimitris, Achlioptas, and Fotis, Iliopoulos. I will begin by briefly explaining the model of computation that we will use in this talk. So there are cases where a computation problem arises that has both huge input and huge output size. So, of course, in those cases, it would be prohibitively expensive for the existing algorithms. Like even sublinear time algorithms wouldn't be enough since we don't have time to give the output. However, in these cases, it is expected that a user would only be interested to see a subset of the output. And to make this more precise, the user has the ability to make queries to the output, as you can see in this picture, and the number of these queries is going to be sublinear in the size of the output. So the algorithm will respond to each of those queries by in turn querying the input in a sublinear number of places. So to answer the query about this red point of the input, it will have to the red point of the output will have to query the input in those two places, for example. In this, this model of computation algorithm was first introduced by Rubenfeld et al. In 2011, and the algorithm's performance is measured by its running time per query, denoted by T, the space complexity that it uses, the space that it uses, denoted by S, and the error probability delta. In order to be able to obtain more refined ranges of these quantities, we slightly generalize the model in this work by adding the fourth parameter, which is the number of queries Q. We do this to add some extra flexibility to this model, and this can potentially allow bounds that use the original model to be further refined. Let me now give an example and at the same time point out an essential aspect of the local computation model. So consider the problem of hypergraph to coloring. So that is, the problem is that we need to color every vertex of a hypergraph either red or blue, such that there is no monochromatic edge. So in a local computation algorithm, the algorithm would answer a set of queries asking for the color of each vertex in a subset of size Q. So the user will make Q queries on Q respective vertices and ask if the color of the vertex in the coloring is red or blue. So what is crucial to note here is that the answers to these queries need to be consistent. So by that I mean that the partial solution that we get has to be extendable to a valid coloring of the graph. For example, suppose that the local computation algorithm outputs red on all those 6 vertices. It would not be an acceptable answer since each of these pairs of red vertices forces the third vertex in their respective clause to be blue, and this will and if this happens, we would get a blue monochromatic edge here. However, note that for each of those 6 vertices, there does exist a valid coloring where it is colored red. In fact, if you take any proper subset of these vertices and require all of these vertices in the subset to be red, this is still extendable to a valid coloring of the entire graph. Let me now introduce a very important tool widely used in proofs that follow the probabilistic method. It is called the Lovasz local lemma, and it's by Erdos and Lovasz from 1975. And is useful in cases like the previous example, when one has to avoid a bunch of non-independent bad events that have some sort of limited dependence among them. So considering the hypergraph coloring example, a bad event would be that a specific hyper edge is monochromatic. This theorem says that if the probability of each bad event is at most p, and its hyper edge overlaps by at most delta other edges, And the product of these of these two quantities is the most 1 over E, then a valid coloring exists. Note that this is like searching for needles in a haystack, since a randomly chosen coloring could have an exponentially small probability of being valid. It's because there's an exponential number of possible colorings, and for example, only a constant number of them could be valid. Even though this result was existential, a breakthrough result by Moser and Tardos about a decade ago made it possible to find such needles in polynomial time, given that the LL conditions were satisfied. Here's what the result says for K-SAT, which is very closely related to the problem of hypergraph coloring that I mentioned earlier. So it says that if each clause shares variables with at most 2 to the k over E other clauses, then it is satisfiable, and the satisfying assignment can be found in polynomial time. So in terms of, if you want to think in terms of hypergraph coloring, you can think of it as hyperedges and sharing vertices. Note here that the dependence between clauses can be described by a graph, which is called a dependency graph, G of V comma E, where V is a set of, the vertex of the graph V is a set of clauses, and there is an edge between two vertices Vi and Vj if and only if they share at least one variable. So the algorithm to find satisfying assignment is very simple. So we start by sampling a uniformly random truth assignment sigma 1, and then we repeatedly resample an arbitrary violated clause C1 until all the clauses in the formula are satisfied. So the question now is, what if we were only interested in learning the truth value of only a subset of the variables? Can we design local commutation algorithms for such settings? The answer to that question was known to be yes. However, this was only based on earlier constructed proofs of the Lovasz local lemma in 1991 by Beck and Alon independently. Even though polylogarithmic time and queries complexity is achievable by simulating these algorithms, there is a major drawback, which is the very restricted conditions on which these results rely on. So to make this more precise, as you can see here, if k is less than 8, then this condition is not even meaningful. So this means that the K-SAT instances for which these algorithms work need to have at least 8 variables in every clause, for example. In this work, we saw that a local commutation algorithm exists even for the much less restricted conditions that the Moser-Tardos algorithm needs. Furthermore, we can achieve both sublinear time and space complexity of n to the theta 1 and n to the theta 2 respectively for any positive theta 1 and theta 2. And the exact bounds also depend on the number of queries that the algorithm needs to make. More formally, our results expressed in terms of K-SAT is what you can see in this slide. So as you can see in this theorem, the smaller the number of queries is, the better the trade-off that we can achieve between the running time per query and the space complexity of the local commutation algorithm. In particular, if you have n to the alpha queries, and the running time per query is n to the beta, the space that you need is n to the alpha plus beta, if alpha plus beta is smaller than 1. Also for polylogarithmic number of queries, we achieve almost the same time and space complexity. Note also that even without a restriction on the number of queries, our theorem gives a meaningful result that improves on prior work. You can see the paper for more details. Okay, let's now move on to the description of our local computation algorithm. This algorithm is going to be a simulation of an instantiation of the Moser-Tardos algorithm. So what do I mean by that? Recall that the Moser-Tardos algorithm, in order for the Moser-Tardos algorithm to work, there was no restriction on which clause or which violated clause needed to be resampled in each iteration. However, for our algorithm, it's going to be crucial that we choose this violated clause cleverly, in order to achieve what we want. So, okay, so what is the algorithm going to do? Suppose that we get a query, we query a variable q1, and suppose that this blue dot corresponds to a clause that contains that variable. And in this picture, I have drawn a radius, a ball of radius r in the dependency graph. I have not pictured the edges, but imagine that these dots are connected by the edges of the dependency graph. And all the black dots in the picture are the clauses that are within distance r from the clause that contains variable q1. Note that it doesn't matter that much which of the clauses containing q1 we choose, as by definition of the dependency graph, all the clauses that contain q1 form a clique. They're within distance one of each other. Okay, so the algorithm proceeds as follows. First, we focus on this ball of radius r, and we first get a partial truth assignment drawn by the underlying distribution of the variables. And this assignment might satisfy some clauses denoted by green here, and might violate some other clauses, the red dots that you can see in the picture. The algorithm now proceeds by resampling the lowest index violated clause that only lies in the current ball that we focus on, of radius r around the first query. So eventually, by simulating the Mozart-Tadros algorithm, all the clauses inside this ball will satisfy, and at this point, the algorithm will output the current truth value for variable q1. Now, as the second query q2 comes in, we similarly form a ball of radius r around it, and now, as you can see, there might be some black clauses here. This means that they contain variables that have not been assigned a truth value yet. So now the algorithm needs to extend the partial truth assignment on these new variables that appeared. This might mean that some clauses will be satisfied and some other clauses will be violated. So now we focus on the second ball of radius r and simulate the empty algorithm until all the clauses in the second ball are satisfied. And note that this might cause some clauses in the first ball, but that are distance 1 from the boundary of the second ball to get violated, and this is just because they will be sharing variables with clauses in the second ball. So at this point, however, the algorithm can output the value for the second query, and move on similarly with the rest of the queries. Now, for the analysis, what we need to show is that the radius r can be chosen in such a way that ensures that both the running time and the probability of error is small. Note that the running time grows exponentially with the radius r, while the probability of error decreases exponentially as well. The latter can be shown by a modification of the witness tree argument of Moser and Tardos in combination with some more recent results regarding its running time. Essentially, it suffices to rule out the possibility that the query variable q1, for which the algorithm has produced an output, will be resampled again at some point later in the execution of the Moser-Tardos algorithm. However, if that happened, it would imply the existence of a path of closed resamplings that has length at least r, as you can see in this picture. So suppose that q1 is a query that the algorithm needs to answer at some point. We would like to bound the probability that after producing an output for this query, the algorithm will ever go back and resample this particular variable. So the reason that this is unlikely is that because when it produces an output, the entire ball of radius r around this query is satisfied. And for the algorithms to go back, there needs to be a sequence of one clause being resampled, violating another clause, etc., etc. And this sequence will have length r, which implies the existence of a witness tree of size at least r, which is unlikely due to the modified witness tree algorithm that I mentioned. Finally, note that the running time per query is linear in terms of the size of its ball, which implies that the total space needed is proportional to the running time per query and to the number of queries. To summarize, we have obtained the first local computation algorithm that works for the general conditions of the Lovasz local lemma, which match the existential Lizard by Erdős and Lovasz. Also, we have showed detailed performance trade-offs between the time and space complexity as well as the number of queries. I would like to note here that our results do extend to other LLL-inspired algorithms that are beyond the variable settings used in the Modest-Azor by the Modest-Azor's algorithm. In terms of open problems, one natural open problem would be if it's possible to obtain a polylogarithmic time and space local computation algorithm for any number of queries under the general LLL conditions, and if there are other applications beyond the variable setting that we can apply this to.